Good morning, dear students. So in the last class, we were discussing the valence bond theory, right? So what all theories we have discussed? We have discussed Werner's theory, right? We have discussed Werner's theory. And the second theory which we have discussed is VBT, valence bond theory. So we have seen the postulates of valence bond theory. So we have discussed about primary valency. We have discussed about secondary valency. Okay, and we have seen the differences also between the primary and secondary valencies. Right. Okay. So today we are going to see the applications. Okay. We are going to see the application of VBT, how we are going to use the VBT. Okay, in the complexes. So let us see. So these are the complexes. So hexaamino cobalt 3. Okay, then we are going to study the property. Okay, then we are going to study hexa florido. Okay, hexafluorido cobalt 3. Again, second. So these are the uh, complexes with coordination number 4. Okay, coordination number 6, sorry, not 4, coordination number 6. So these two complexes we are going to study with coordination number 6. Okay, and these two complexes, that is, first one is tetrachloridonickelate. Okay, so this is your coordination number 4, and tetracyanidonyl nickel. Okay, so this is also 4. So these are the complexes which we are going to study, and we are going to study its properties. Okay, so these four are important. So anyone they will ask in exam. Okay, any one of this will be asked in the exam. So mark this as important. Okay, so mark this as important. So out of these four, any will be asked. Okay, so let us start first with the structure of hexaamino cobalt. Okay, let us start with the structure of hexaamino cobalt. Okay. Let me take a blank slide. Okay, now here, so let us see the applications of VBT. Applications of VBT. Okay, so the first one is in octahedral complexes. In octahedral complexes. Okay, so with coordination number 6. With coordination number 6. Okay, so we are going to see cobalt NH363 plus. Okay, so this is a complex. So now, what is the atomic number of cobalt, students? What is the atomic number of cobalt? It is 27. Right, it is 27. So argon 18. Okay, then comes your 3D 7 and 4s2. 18, 19, 20 and 27. Is it? Okay. Now here, can you find the oxidation state of cobalt here? So cobalt NH3 6 3 plus. Okay, so cobalt X plus 6 into ammonia is 0. So it will be 0. Okay, and is equals to plus 3. So X will be plus 3. Okay, so the charge on the cobalt is plus 3. So cobalt, when it loses plus 3 electrons, how it will lose plus 3 electrons? So it will be again argon 18. Okay, so it will lose its electron from s orbital and the last electron from d orbital. So it becomes 3d6. Okay, it becomes 3d6. So the oxidation state of the central metal ion, okay, that is the cobalt, is plus 3. So let us write the let us write the electrons. Okay, so 3d6. So 1, 2, 3, 4. So 5 orbitals, right? So it has 5 orbitals, d orbitals. So 3d. Okay, so next is what? 3D. After that will be your 4s orbital, and next we are going to use the 4p orbital. So this is the way you have to write. Okay. Now fill up the electrons. Fill up the electrons. So 6 electrons are there. So 1, 2, 3, 4, 5, and 6. So you know that okay, whenever you are filling the electron, first the electron should be filled singly, right? First the electron should be filled singly, and then the pairing will takes place. So that you know. Okay. Now, so this is about the central metal atom. So this is the oxidation state. So when it loses 3 electrons, so like this, you have to write the hybridization. Okay. Now, under the influence of ammonia. So ammonia is a strong field ligand. Okay. So ammonia is what? It is a strong field ligand. Okay. So there are something called as strong field ligand and something called as weak field ligand. So ammonia comes under strong field ligand. So when cobalt, when it comes under the influence of ammonia, which is a strong field ligand, what will happen? Okay, now when you see the splitting of orbitals, okay, when you see the splitting of orbitals, okay, so your three T2G and your EG orbitals will be there, right? So when it comes under the influence of ammonia, okay, that is your ligand, what will happen? The electrons will pair up at the ground itself. Okay, it is the distance is very large. Here the distance is very far. So because of that, what is happening? The electron pairing takes place at here only. So what will happen now? So when it comes in contact with a strong field ligand like ammonia, the electrons will get paired up in the 3D orbitals. Okay. So how does the pairing takes place? So I'll show you. So here again, so under the influence of 1, 2, 3, 4, 5. Okay. So this is 3D, this is 4s, and this is 4p. So let me change the color. So the electron filling, so 1, 2, 3, 4, 5, 6. Right. So how many ammonia are there? How many? 6. 6 ammonia. 6 ammonia means 2 electrons each. So how many? So these are 1, 2, 3, 4, 5, 6. So these are the empty orbitals, okay, where ammonia can occupy this. Okay, so these orbitals are occupied by ammonia. Now, what is the hybridization? What is the hybridization? What all is left here? So your D2, okay, D2, then this is S, and P3. So D2 sp3. Okay, D2 sp3 hybridization. So what is the hybridization? D2 sp3 hybridization. Okay. So the hybridization of the hexaamino cobalt complexes D2 sp3 hybridization. So why? Because when it comes in contact with the ammonia, okay, as it is a strong field ligand, so pairing of electron takes place at the T2G level itself. And the empty orbitals which are left, so these will be occupied by the 6 ammonia. 6 pairs of ammonia. So 1, 2, 3, 4, 5, 6. Okay, so the hybridization resulted is D2sp3. Now these hybrid orbitals will overlap with the ligand orbitals, right? So these orbitals, so these empty orbitals, they are occupied by what? These are occupied by the ligand orbitals. Okay, so let me write it here. Next point. So hybrid orbitals. Okay, so these are the hybrid orbitals. Okay, so these are the hybrid orbitals. So these hybrid orbital, they overlap with with ligand orbitals. Okay, with ligand orbitals. And how many coordinate bond it forms? It forms 6 coordinate bonds and forms 6 coordinate bonds. Okay, so how the 6 coordinate bonds are formed? See here again. So 1, 2, 3, 4, 5. So this is 3D, 4s, and 4p. Okay, so again the filling of electrons. So these are the paired electrons of your cobalt. Okay, now your this, what is that? Uh, Ligand. Okay, so the ligand. So these are filled by the ligand orbitals. So how they are filled? So I can represent it by X. So X, okay. So these are filled up by ligand orbitals. Okay. So these are the six pairs of electrons from NH3 ligand. Okay. So from NH3 ligand. So what type of hybridization it is showing? Yes, it is showing you a D2sp3 hybridization. So let us see the properties now. So let us see the properties. So this is a compulsory 3-mark question. So any one of the complex will be asked. So you have to write. So what are the steps? So you have to write the electronic configuration, then you have to write the electron distribution. Then when it come in contact with the strong field ligand, so what will happen? Electron pairing will takes place. What will happen? Okay. So that all things you have to mention. You should mention, and then you have to write the properties. So what is the geometry of the property? What is the geometry? So geometry depends on what? The coordination number. So how many ligands are around the central metal? 6. So whenever it has a 6 coordination number, it will undergo what type of geometry? It will undergo octahedral geometry. It will show octahedral geometry. Then magnetic behavior. What is magnetic behavior? Whether they are attracted by the electromagnetic field, or that is magnetic field, or they are repelled by the electromagnetic field. Now here you can see that all the electrons are paired. Right, here you can see here at the bottom here. Okay, when you consider this, so you can see that all the electrons are paired. There are no unpaired electrons. So because all the electrons are paired, okay, because there is no availability of any unpaired electron, okay, these are what? These are diamagnetic. These are what? Diamagnetic. Okay. And what is the hybridization, students? Hybridization Hybridization is D2sp3. Okay, it is D2sp3. And what type of it is showing? It is showing it is using what type of orbitals? It is showing it is using inner d orbitals, right? So it will show inner orbital complex. Okay, inner orbital complex, or it is called as the low spin complex or low spin complex. Okay. So it will show inner orbital complex or it will show low spin complex. Is it clear? So these things you have to mention. Okay, these all things, whatever I have discussed, it should be mentioned. Okay, so important, very important, ask for 3 marks in the exam. Okay, is it clear? So let us see one more. Okay, second octahedral complex, that is COF6. Okay, COF6 3 minus. So second one. Okay, now here find out the oxidation state of cobalt. So COF6 3 minus. Okay, X plus 6 are there. Each fluorine is -1 equals to -3. So X is equals to -6 is equals to this. X is equals to -6 plus 3. So X is equals to 3. So X is equals to 3. So cobalt again. So cobalt is 27. So argon 18. Okay. Then 3d7 and 4s2. So cobalt, when it shows +3 oxidation state, it becomes argon 18 3d6. Okay. Now, as the central metal atom is cobalt and its oxidation state it was +3. So the electronic configuration becomes, okay, so again write the electronic configuration. So 1, 2, 3, 4, 5, then comes your 4s and then comes your 4p. So this is 3d, 4s and 4p. Now fill up the electrons again. So how many electrons are there? 6 electrons are there. So again 1, 2, 3, 4, 5 and 6 electrons. Now what? So this is the cobalt. Okay. Now we have written the electronic configuration for cobalt. Now under, so what is their ligand? Your F, that is your fluorine. So under the influence of, F, that is your fluorine. Fluorine is termed as a weak field ligand. Okay, it comes under weak field ligand. Okay, so what will happen? Electron pairing does not takes place. Electron pairing does not takes place. Okay, so because it is a weak field ligand, electron pairing does not takes place. Why? What is the reason? I'll tell you. So again, when the splitting takes place, okay, now here the distance between this is very less. Okay, so what will happen? The electrons, Now, after filling the 3 electrons, okay, if the distance is high, okay, if the distance is more, so the next electron to go at the above, it is difficult, right? Like in the previous case when we had strong field ligand. So what was the in strong field ligand? So what was happening in strong field ligand? Under the influence of strong field ligand, the electrons got paired down only. Why? Because the distance is large. Okay, so for the fourth electron to go, the distance is more. So because of that, it is getting paired here itself. Okay, this is under the strong field ligand. Now, when you have weak field ligand, what will happen? When the splitting takes place, okay, of the d orbitals. So I'm representing these d orbitals only. So d orbitals, they are divided into T2G and EG orbitals. So three orbitals down, 2 orbitals up. Now that time, what will happen? The distance is very less. So for the fourth electron to get uh, okay, so it can easily go above. So how many electrons became? 1, 2, 3, 4, 5, and again 6 here. Okay, so like this. So the under the influence of the weak field ligand, that is your F minus ligand, electron pairing does not takes place in 3D orbitals. So in 3D orbitals, the electron pairing does not takes place. Okay, so what happens? Thus what will happen? Thus Thus what so there is so what will happen? So for fluorine we have to make orbitals, so we have to make use of outer d orbitals. Okay, so we are going to use the outer d orbital. So let us see. So let us see if I write the electronic now here, just see. So here, so how many? 3, 4, and 5. Okay, then is your so 3D, 4S, and 4P. So under the influence of what will happen? Now what is happening here? So under the influence of the weak field again, like your F minus ion, the electron pairing does not take place in 3D orbitals. Thus we are going to use the outer d orbital complex. Now here see, how many fluorine atoms are there? 6. And how many they are available? 1, 2, 3, 4. We require 2 more. For those 2 more, we are going to use the 4D orbitals. Okay. So next 4D orbitals. So now here, so what will just write the electronic configuration here. So 1, 2, 3, 4, 5, and 6. Now here, so these orbitals. So 1, 2, 3, and 4, and 5. So these orbitals, these are occupied by what? So what is hybridization? So S, this is P3, and this is D2. Okay. So this is what? This is a outer orbital complex. Okay, this is a outer orbital complex, or it is called as high spin complex, or it is called as what? High spin complex. Okay, so this here what will happen? Here your uh, so these are the hybrid orbitals which are so these hybrid orbitals are what? So these hybrid orbitals, okay, so with filled will be filled with ligand orbital. Okay, it will be filled with ligand orbital and forms 6 coordinate bond and what 6 coordinate bonds. So here, so let us write that now. So let us write. So first is your 1, 2, 3, 4, 5. Then your 4S, 4P, and this is your 1, 2, 3, 4, 5. So this is your 3D, 4S, 4P, and 4D. So 1, 2, 3, 4, 5. Okay, 6. So these are your orbitals which are made used by your central metal atom. Now, so these are the orbitals which will be used by the ligand orbitals. So here, let us write the ligand orbitals. So it is 1, 2, 3, 4, 5, and 6. So these are the 6 pairs of electrons, okay, from 6 fluorine ligands. Okay, so the hybridization is what? So this is a high spin complex or the outer orbital complex. Why it is called as outer? Because we are making use of the outer d orbitals. Okay, why the pairing is not taking place, students? Because the fluorine is a weak field ligand. Because fluorine is a weak field ligand, the electron pairing does not take place because the distance is very less. So the fourth electron, when the pairing wants to take place, it can go to the above orbital. So the pairing does not takes place. Okay. Now let us write the properties now. Let us write the property. Can anyone tell me what will be the geometry of this? What will be the geometry of this, students? And what is the magnetic behavior? Magnetic property. What is the geometry? What is the magnetic behavior? Now you might have understood. So you can answer. What is the geometry? So cobalt is in the center and it is forming 6 coordinate bonds with the fluorine. So what type of geometry it will show when you have a coordination number 6? So the ligands, number of ligands around the central metal atom are 6. So what will be the coordination, students? It will be a octahedral geometry. Yes, very good. Yes, baby has answered it. So it is a octahedral geometry. Okay. Then what is the magnetic behavior? Can anyone discuss about magnetic property? So what happens? So look at this. Look at this and tell me electrons are completely paired or electrons are not paired. Yes, electrons are paired or electrons are not paired. The electrons are unpaired here. You can see here the electrons are single here. So whenever there are unpaired electrons, okay, that is due to the presence of this unpaired orbital. So how many unpaired electrons are there? 4. You can see here 4 unpaired electrons are there. Because of that, it will show paramagnetic behavior. Okay, paramagnetic behavior. So whenever all the electrons are paired, okay, they will show what? They will show diamagnetic behavior. Whenever the electrons are unpaired, okay, they are singly, they are left singly, then they will show paramagnetic behavior. Yes. What is a hybridization? What is a hybridization? It is sp3d2. Okay, that is a outer orbital complex. Okay, it is a outer orbital complex, or it is a high spin complex. Okay, or it is a high spin complex. Is it clear? So very important. So we have completed 2 complexes. Is it clear up to here? Yes, is it clear up to here, students? Any doubts in this 2 complex? Very important. Anyone among the 4 will be asked. Okay. Mostly they will ask the coordination number 4, 5, 6 itself. So is it clear? Okay, fine. So next is so we have completed the octahedral complexes. Next is the tetrahedral complexes. Next is what? Tetrahedral complexes. Tetrahedral complexes means with coordination number 4. Okay, with coordination number 4. Okay, now, so which is the complex? So nickel tetracyano 2 minus. Okay, so this is the this. So yes, first, what is the first step? First step is find the oxidation state of nickel. Okay, find the oxidation state of nickel. So X plus 4 into minus 1 is equals to minus 2. X minus 4 minus 2, X is equals to plus 2. Okay, now, so nickel is plus 2. So nickel, first we'll write nickel is 28. So argon 18, 3d7, 3d8, 4s2. So 18, 19, 20, 28. Now nickel, when it shows plus 2 oxidation state, it is again argon 18, okay, and 3d8. Okay, argon 18 and 3d8. So let us write the, so 1, 2, 3, 4, 5, 4s and 4p. Okay, so this is 3d, 4s and 4p. Okay, fine. So now how the electron pairing takes place? So again 1, 2, 3, 4, 5, 6, 7 and 8. Okay, so this is the electron distribution of the nickel. Now, which is the cyano? Okay, so cyanide is a strong field again. So what will happen? So under the influence of the strong field ligand, okay, under the influence of the strong field ligand, that is your cyanide ion, what will happen? Electron pairing will take place or no? Yes or no? So cyanide is a strong field ligand. So what will happen? Electron pairing will take place, yes or no? Yes, it will take place. Very good. So electron pairing will take place. So under the influence of the strong field ligand, neither like your cyanide ion, the electron pairing will take place. So let us see. So let us see. So 1, 2, 3, 4, 5. So 4p and here is your 4s and 4p. So 3d, 4s and 4p. Okay, let us write the electronic distribution. Why? Why the electron pairing it takes place? Because when the d orbitals are splitting, oh, fine. Okay, when the d orbitals are splitting, they're splitting into T2g and EG. Okay, and what is happening here? The distance will be large. Okay, whenever you have a strong field ligand, the distance will be large. So after the three electrons are occupying a single orbital, the fourth orbital to go above is very difficult because of the large distance. So the pairing takes place here only. Once 1, 2, 3, 4, 5, 6 orbitals are filled, then no other option. So the two electrons should go above itself. Okay. So let us see now. So let us see. So how the electron takes place. So here 1, 2, 3, 4, 5, 6, 7, and 8. So like this, the electron takes place. Now here, how many cyanide are there? 4 cyanides are there. So 1, 2, 3, and 4. So can you tell me the hybridization here? Can anyone tell me the hybridization? So four ligands, so four set of ligand orbitals will occupy four pairs of. Yes, can you tell me what will be the hybridization? What is the hybridization by seeing this? Yes, try. If it is wrong, no problem. You have to try. Yes, what is the hybridization? So which orbitals they are going to occupy? This is what? This is a D, S, and P2. So DsP2 hybridization. Can you tell me, is it an inner orbital complex or outer orbital complex? What type of complex it is? What type of complex it is? It is a inner orbital complex. Why? Because we are making use of inner d orbitals, right? Inner orbital complex, or it is called as the low spin complex or the low spin complex. Fine. Now here, now what will happen? So nickel tetracyano cyanido, okay, 2 minus. So this is a low spin complex. So what will happen? Now the next step is, so write the 1, 2, 3, 4, 5. So, and these are the three. So 3D, 4S, and 4P. So how the electrons will, so these are the 1, 2, 3, 4, 5, 6, 7, 8. So these are the orbitals of your nickel, and 1, 2, 3, and 4. So these are the orbitals of your ligand metal, ligand orbitals. Okay. So the hybridization is D2. That is the, so these are the four pairs of ligands from four cyanide ligand. Okay. So these are the four pair of electrons, not ligands, four pair of electrons from four cyanide ligand. Yes. Now, can you tell me the geometry? Can anyone tell me the geometry of this? Can you tell me geometry of the students? Try. So when you have a coordination number 4, okay, when you have a coordination number 4, what will be the geometry, students? Try. What will be the geometry? Not okay, not tetrahedral. It will be square planar. Okay, it will be square planar. So square planar, nickel will be at the center, and the four cyanides at the four corners of the this. Okay. So cyanides at the four corners of the, so this is the your square planar complex. Can you tell me the magnetic behavior, magnetic property? Can you tell me the magnetic property by seeing this? Yes, by seeing this, or can you tell me what is a magnetic property? Is it the electrons are unpaired, paired? Yes, it is a diamagnetic. Very good. So it is a diamagnetic. Okay, diamagnetic because all the electrons are paired. Okay, all the electrons are paired. So, and what is a hybridization? It is dsp2 hybridization, and we are making use of the inner orbital complex. Is it clear? Is it clear, students? Okay, so anyone will be asked. Out of four, anyone will be compulsorily asked. So these all things, whatever I have discussed, it should be mentioned. Okay, it should be mentioned. Okay, let us go for the last complex. Okay, last complex, that is your NiCl4. NiCl4. Okay. So again, NiCl4 minus 2. So nickel plus 4 into minus 1 equals to minus 2. So X is equals to plus 2. So again, the oxidation state of nickel is what? Plus 2. So nickel is 28. So it is argon 18, 3D8 and 4s2. So nickel plus 2, it is argon 18 and 3D8. Argon 18 and 3D8. Okay. Now, let us write the electronic configuration. So 1, 2, 3, 5. 4s and then another 4p. So this is 3D, 4s. Okay. So 1, 2, 3, 4, 5, 8. Okay. So these are the 3D. Okay. So this is a 3D8. Okay. 3D8 system. Now here, so now which is the ligand? So ligand is chlorine ligand. So this chlorine ligand, it is a weak field ligand. Okay, so under the influence of the weak field ligand, like your chlorine ligand, okay, chloride ion. So what will happen? The electron pairing will take place or no? Electron trailing, yes, does not takes place. Very good. So now you might have understood. So which are the strong field ligand? So here we have discussed. So remember that strong field ligands we have discussed. One was the ammonia, another was the cyanide ion. So whenever the strong field ligands are there, electron pairing takes place. Okay, electron pairing takes place. And whenever you have weak field ligand, so which are the weak field ligand? Weak field ligand like your F minus fluoride ion, chloride ion, what will happen? The electron pairing does not take place. Okay, electron pairing does not takes place. Okay, fine. Now here chloride ion is a weak field ligand, so electron pairing does not take place. So let us write the hybridization again. So this is 3D, 4s, 4p. Okay, so let us put the electrons now. So again, so 1, 2, 3, 4, 5, 6, 7, and 8. Now, how many chlorine atoms are there? 4. Now, there are availability only 3. So, what we require? The outer orbitals. Okay, so 1, 2, 3, 4, 5. So, we are making use of what? So, we are going to make use of 1, 2, 3, and 4. Can anyone tell me the hybridization now? Yes, can anyone tell me the hybridization? So this is 4D. Can anyone tell me the hybridization, students? Yes, can anyone tell me the hybridization? So this is what? This is S. These are P3 and D. So sp3d. Okay. sp3 1 2 3 4 5 6 7 8. S. No. 1 2 3 4. No, 4 is required. Yes. So we are not making use of the correct. Wait. Not require. So 1 2 3 4. So here it is required. So only sp3. Okay, so it is only sp3. Okay, sp3 hybridization. Right, so only four orbitals are required to occupy the four pairs of four electron pairs of the four that is from the four ligands. Okay, that is your chlorine ligands. Now, so each hybrid orbitals will overlap with the filled d orbitals. So let me write the 1, 2, 3, 4, 5. So here 3, 4, 5, 6, 7, and 8. Okay. Now the four pairs of chlorines, they are occupied by what? So 1, 2, 3, and 4. So this is what? So this is the, so these are the four pairs of electrons from 4 Cl minus ligands. Okay. So the hybridization is sp3. Can you tell me the geometry? Can you tell me the geometry, students? What is the geometry? It is a square planar. Yes, very good. So geometry is square planar. What is the magnetic behavior? Magnetic behavior. Magnetic behavior, it is unpaired electrons are present. So because of it, it is a paramagnetic. Okay, it is a paramagnetic. What is hybridization? sp3 hybridization and sp3 hybridization, and it is a high spin complex. Okay, it is a high spin complex. Okay, fine. So, this is about your uh, VBT. Okay, is it clear up to here? So, what are the limitations? Okay, so VBT, it could explain what? It could explain the okay. Now here, so what were the limitation of this? Okay. So because VBT, what would it, VBT could explain the geometry and the magnetic behavior. Okay. So, but it could not explain the color of coordination compound. So where this valence bond theory could not success. Okay. So there were some limitation for this valence bond theory. So it could not explain the color of the coordination compound. Okay, and it could not explain the magnetic behavior based on the geometry. Then it could not explain between the strong field as the weak field ligand. And phase two, and it also could not explain Now, when you tell geometry 4, why it should not occupy tetrahedral complex? Okay, so we can have also tetrahedral geometry, but it could not explain the exact geometry of the complexes with coordination number 4. So these were some of the drawbacks, or you can say limitations of the valence bond theory. Okay, why some of the complex could show the inner orbital complex, and the same metal could explain the, we have seen. Okay, just now we have seen. So cobalt, when it comes in contact with the NH3, that is this particular complex. And when we see this particular complex, okay, what was explained here in the first complex, okay, in the first complex, it could show a what? It could show a low spin complex. Okay, it could show a low spin complex, or it could show the inner orbital complex. And in COF6 3 minus, okay, it could show the outer orbital complex. So for the same central metal atom, it would see show the different orbital complexes. So this could not be explained with the valence bond theory. So because valence bond theory could not be satisfied, so next came the CFT. Okay, next came the CFT, that is your crystal field theory. Okay, crystal field theory. So crystal field theory, so let us discuss that crystal field theory in tomorrow's class. Okay. Any doubts about VBT? So in the last class, we have discussed about Werner's theory. Okay. And then we have discussed today about the VBT. So complexes, the four complexes, whatever I have discussed, it is very important. So please go through all the complexes, four complexes, and go practice them. Please practice them. So with coordination number 6, we have seen two complex. With coordination number 4, we have seen two complex. So please go through the things. Okay. Fine. Anything? Any doubts? Yes, any doubts, students? Okay, fine. So the remaining things, CFT and all, we'll be discussing in tomorrow's class. Thank you.